It's 4 a.m. on a Saturday. The date is May 9th, 2026, and I thought, what better time, to do a power series problem set. This problem set will be 8 problems, featuring how to find the interval of convergence of a power series, the radius of convergence. We're going to do some diversion tests. We're going to do some ratio tests, and there will be some limits as well. There will also be some inequalities too. Um, and I do believe there's a McLaurin series. So it's gonna be 8 problems, very minimal, light editing, and yeah, game on. So this first question, it says to determine the radius and interval of convergence of the power series starting at 1, a summation from 1 to infinity for x raised to the power of 2 times k plus 1 over 13 raised to the power of k minus 1. The best way So the best way to evaluate this would be to use the ratio test. And just let me check really quickly. I'm recording, right? Okay, cool, because I've been burned before. So the best move right here is to do the ratio test. And I know that I should use the ratio test because of the presence of both x raised to the power of 2 times k x raised to the power of 2 times k plus 1 and 13 raised to the power of k minus 1. And this gives it away because if we think about what the ratio test actually is, well, it's going to be a limit that involves division, and that's going to cancel most of the exponents that we're dealing with out. So go ahead and write out the rule for the ratio test. Hmm. Let me be clear, this is a subscript, as is that. Let me just double check something really quickly. I'm just checking out my formula. Okay. So, like I said, the presence of the exponents sort of gives it away because of the division step in the ratio test. It's going to cancel most of that out. And whenever there's a k in the exponent of a fraction, especially when it's linear, like 2 times k plus 1, uh, or k minus 1, the ratio test is going to simplify it. Now, the ratio test right here, it says that we're gonna take the limit as k approaches infinity for the absolute value of a sub k plus 1 over a sub k, and that's going to equal L, our limit. Now, if the limit is less than 1, then the series converges, meaning it the terms add up to a finite sum. That's what converges means. And if the limit is greater than 1 or it's infinity, then the series diverges. And if the limit is equal to 1, then the test is inconclusive and we're going to have to do something else. It should be said that I don't think I've mentioned this before on my channel. Um, for any series to even have a chance of converging, which again, converging means that the summation adds up to a finite number. So for any series to even have a shot at converging, the terms that we're going to be adding together need to be getting smaller and smaller and eventually approach zero. Because if the terms don't like approach zero, then inevitably the sum is going to be infinity because it's just going to be getting larger and larger. You're just going to be adding up larger and larger and larger numbers forever, and that's going to be infinity. And if the numbers are getting smaller and smaller and smaller, well, that's going to approach zero, and it'll eventually fizzle out, and then you can add up all of the partial sums up until zero, or even including zero if you'd like, um, and then the series will converge. So for the series to have a shot at converging, the partial sums, the terms need to approach zero. Let's go ahead and prepare for the ratio test. And we'll do this by identifying a sub k and a sub k plus 1. Well, a sub k, we have it right here in our summation. It's going to be that whole thing. Then a sub k plus 1, all we have to do to get this is just plug in everywhere that you see a k, you just plug in k plus 1. So see how there's a k right here in this exponential place? Well, instead of k, we're going to put k plus 1, and it's going to be parenthetical. Okay, and then this is going to simplify to, well, we can distribute that 2 in the numerator, so it's going to be 2 times k plus 2. Then at this point we can drop the parentheses, that's going to be plus 1. And then we'll move forward by evaluating the denominator. 13 k plus 1, we could just really just drop those parentheses and then combine like terms in this next step here. Let's see. So that's going to be 2 times k plus 3 in the numerator there. And then in the denominator, well, these are going to cancel, and we're just going to have 13k. So now at this point, identified our we've identified our a sub k and our a sub k plus 1. So we need to apply the ratio test. So we'll take the limit. Up top, we're going to have a sub k plus 1. And then on the bottom, we're going to have just a sub k. And of course, this is a complex fraction, so we'll have to reciprocate. So at this point, what I like to do is I like to regroup everything. Um, it's just easier for me to see what's going on, to like put terms together that make sense going together. And here's what I mean by that. We have the limit as k approaches infinity, and it's still going to be the absolute value. But I'm going to put these x's, these x's and these 13s together, um, in their own rational expressions, just because it just makes more sense to me when canceling things out. So we have x raised to the power of 2 times k plus 3 in the numerator, and then in the denominator we'll have x raised to the power of 2 times k plus 1, and then this will be multiplied to 13 raised to the power of k minus 1 over 13 over, excuse me, over 13 raised to the power of k. So now we can apply one of our laws of exponents here. And I could write this out. Now phi and lambda in this case, these are just placeholder variables. They're just meant to show that if you have x raised to the power of b, any number, let x and let phi and lambda represent any number, right? If you have x raised to the power of phi over x raised to the power of lambda, that's the same thing as x raised to the power of phi minus lambda. So what will we have? X raised to the power of 2 times k plus 3 minus 2 times k plus 1. Well, and this is going to be multiplied to 13 raised to the power of k minus 1. Oops. K minus 1 minus k. And there should be some parentheses here. Okay. Well, what's going to happen? Distribute this negative sign. Drop the parentheses here. This is just going to become 13 to the power of negative 1. Whereas, well, that's going to become negative. So we're going to get cancel, cancel. because 2k minus 2k is going to be 0. Um, then we'll have 3 negative, no, yeah, no, yeah, it's going to be 3 minus 1, and that's going to be 2. So the result, let me, limit as k approaches infinity. Oh, that's going to be x raised to the power of 2 times 13 raised to the negative first power, I believe. We can manipulate this algebraically. The limit as k approaches infinity of x squared times 1 over 13. All right, and then that's going to be the same thing as the limit as k approaches infinity of the absolute value of, you could just throw that x squared on top. So x squared over 13. Well, now we're in a place where we can find the radius of convergence. For the series to converge, we're going to look at our constraints and our rules for the ratio test here. In order for the series to converge, the ratio test requires that x squared over 13 is to be less than 1. Well, we need to figure out if this is true. So we have an inequality here, and we need to isolate x. So if we multiply both sides of the inequality by 13 to get x by itself, we're going to have, let's see, 13 times x squared over 13. These 13s are going to cancel out. Inequality sign is going to stay the same because we're not multiplying or dividing by a negative term. So we will multiply this 1 by 13. So we'll just write in 13. And then we're going to have, let's see, x squared is less than 13. Then we want to take the square root of x squared. Cancel, cancel. Then that means that we have to take the square root of 13. And so that's going to give x is less than the square root of 13, I believe. So it was the absolute value of x. So let's just honor that. We'll say the absolute value of x is less than, so that just means it's distance from 0. So if the absolute value is the distance from 0, so even the negative, when something's in an absolute value brackets, it can only ever be positive. So it's just the distance of 0. It does not discriminate which direction, whether it's negative or positive. It's the absolute value of the units from 0. So even -2, like if you have -2, the absolute value of -2 is just 2. Because if you think about a number line and you go to the left direction, negative, it doesn't discriminate whether the number is positive or negative. It just wants the absolute value. So what's the absolute value of -64? Well, it's 64. And so that's what that means. But the absolute value of x is less than 13. And well, that means that the radius of convergence is going to be the square root of 13. So we'll use r to denote the radius of convergence, and the radius of convergence is the square root of 13. So now we have to find the interval of convergence. In other words, so we know the radius, the distance of for see how can I explain this. What does it even mean? The radius of convergence. Okay, well, the radius of convergence is how big the radius is for it to be true that the series converges. Whereas the interval of convergence is it's it's the interval of numbers where the series does not blow up. So it's the zone of numbers for which it is true that the series converges. So now we want to find the interval of convergence, and we're going to do this by looking at our inequality. The interval of convergence asks us whether or not, well, it indicates whether or not the starting number and the ending number, the first and the second number on the interval are included with whether or not the series converges or not. Do those numbers are those numbers included in the safety zone and where the values for the series don't blow up? Do those numbers include convergence or not? So basically, we have this inequality, right? The absolute value of x is less than the square root of 13. This is an open interval. This gives us the open interval. The open interval that it gives us is negative root 13 and root 13. Those are the numbers on the number line. Between these two, all of the values that are put into the series will result in the series converging. But we need to know, what about these are the endpoints. So do the endpoints also cause the series to converge? Is it an open interval or is it a closed interval? So we need to check that the endpoints to see if they should be included within the interval of convergence. So to do this, we're going to test, we'll test x equals root 13. So we're going to substitute root 13 back into the original series. Here's our original series up here. So instead of x, we're going to put root 13, which they're going to raise it to the power of 2k plus 1, and we'll keep the denominator the same. I just realized that the 13 there looks terrible. Let me just fix this, because what good is the math if you can't read it, right? Root 13 raised to the power of 2 times k plus 1, all over the denominator 13 raised to the power of k minus 1. Okay, well, we can look at the numerator, and we can split this using this exponential rule, which I'll write out in blue. And I'll keep rolling with the Greek letters there. We got x raised to the power of phi plus lambda. It's the same thing as x times, yeah, x raised to the power of phi times x raised to the power of lambda. Exact same thing. So what does that mean for our numerator? That means that the numerator can be, it could be rewritten. So honestly, I'll just put a comma. So root 13 raised to the power of 2 times k plus 1 is the same thing as root 13 raised to the power of 2 times k times root 13 raised to the power of 1. So that means that we can rewrite the series so that numerator is going to become, well, let's see. Okay. Um, so the numerator is going to become 13 raised to the power of k, and we'll unpack that in a second. Let me just write this out here. Times root 13 all over 13 raised to the power of k minus 1. And the reason for this is because if we look at this here, root 13 raised to the power of 2 times k, remember that a square root cancels out. So, let's see. If I have like the square root of x, if I have the square root of x raised to the power of 2, that's going to equal x because there's an index 2 in here and these are going to cancel. And so that means that 13 is just going to be raised to the power of k. Now, let's see. We could break this up. We could break this up and I'll make this its own rational expression so it's a little bit easier to see what's going on. Yeah, okay. Times root 13. So this is going to be the same sort of thing that we did up here with well, we have the same base in the numerator and the denominator, the base being 13, raise the power of k in the numerator and then raise the power of k minus 1 in the denominator. And we could just disregard this root 13 because this is going to be 13 raised to the power of k minus k minus 1. And let's see, k minus k minus 1. This is going to become a negative k. This is going to become a positive 1. So what's going to end up happening is we're going to have the summation from k equals 1 to infinity. Oh no, there's not going to be a rational expression anymore because this is just going to become 13 because it's just raised to the power of 1. So that the denominator just goes away. So we're going to have 13 times root 13. Now root 13, we could just write it like this. So if we look at the summation from k equals 1 to infinity for 13 times root 13, literally every single term in the series is going to be exactly the same because there's no k, there's no variable k in this expression here. In this expression here, in the summation, there's nothing to plug in k for. So we could plug in k equals 1, 2, 3, 4, 5, all the way up to infinity, and it's still going to be 13 times root 13. Now, uh, let's see here. 13 times root 13, that's going to roughly equal 46.87, right? I think. And the sigma notation is literally telling us to do 46.87 plus 46.87 plus 46.87 plus 46.87 infinitely many times. So not only are these terms, they're not getting smaller, which is that's kind of like a necessity if you're checking to see if you want to see if the series converges or not. The partial sums need to be getting smaller and smaller and smaller. That is not the case here. It's just going to go up to infinity. So not only are these terms not getting smaller, but they're not changing at all. And the total sum, it's just getting larger and larger and larger as you add, because the limit of the terms, well, the limit of the terms, it's infinity. So, okay, wait. Because the limit of the terms is not zero, it does not zero out. The if we applied the limit test to this, not the limit test, what am I talking about? We applied the the divergence test to this. So the divergence test is like the divergence test, it's like so we put in the ratio test. This is what we got. If we put the divergence test is like the summation from k equaling 1 to infinity for a sub k, which in this case our a sub k is 13 times root 13. And if you look at the limit of the terms as k goes to infinity, if the limit as k goes to infinity does not equal 0, then the series a sub k diverges. Well, we could just check this, use like one quick glance with the divergence test. This here, one one quick check intuitively just tells us immediately that this diverges. So basically, you take the limit and you find out what happens to the terms. So as k gets really large, if the limit is not 0, then then the series diverges, and that's it for the limit test. But if it's exactly 0, then the limit test is inconclusive and you have to use another test to find it. But we could just look at this and we could say, okay, well, this limit is going to be infinity. So in our specific problem, we simplified our a sub k, and a sub k is 13 times root 13. And, well, let me see. I could write out a quick test here. So the limit as k approaches infinity for 13 times root 13, this is just going to be 13 times root 13. And since 13 times root 13 is not 0, then the limit diverges. And since we're adding up a constant value infinitely many times, the series diverges by the divergence test. So now what we'll do is we can, we'll check, well, we plug in our first um, endpoint, which was root 13. Then we'll plug in our second endpoint, which is going to be negative root 13. And spoiler alert, that's just going to give us the same exact thing, only there's going to be a negative in front of the 13. So it's going to be the summation from k equaling 1 to infinity of negative 13 times root 13. And this is going to diverge for the exact same reason, because you're just going to be infinitely adding negative 13 times root 13 together forever. And that's not going to approach zero. So by the limit, by the divergence test, the limit as k approaches infinity for negative 13 times root 13, well, that's going to be negative, let me see if I could put a negative there, and it's going to be negative 13 times root 13, and that is going to prove to diverge by the divergence test. And so what that means is that the interval of convergence, which I'm going to denote with an I, with a capital I, is going to be, well, that's going to be a, a parentheses, so a left parentheses, or a left parenthesis. I'm not sure, I don't think it's plural. It's going to be a left parentheses, a left parenthesis, negative root 13 for the first endpoint. The second endpoint is just going to be 13 with a parenthesis. So they're not included. Negative 13 and negative root 13 and root 13 are not. Negative root 13, the interval of convergence is negative root 13 to root 13. Therefore, everything sandwiched between these two values, not including these values, but everything sandwiched between them, is going to be a safe zone for convergence for this series. And um, so yeah, so this is going to be the interval of convergence, and so yeah, that's how you solve that. In short, the radius of convergence is root 13. The interval of convergence is negative root 13 to root 13. The values between those, not including those. So this next problem here in the problem set says to use the power series f of x equals the natural log of 1 minus x equals the negative summation of k equaling 1 to infinity for k raised to the, excuse me, for x raised to the power of k over k, for negative 1 being less than or equal to x, which is less than 1, to find the power series for the following function, which is centered at 0, given the interval of convergence of the new series. And our function here is it's f of 5 times x equals the natural logarithm of 1 minus 5x. So yeah, like what's going on? what what are we even doing? What's even being asked? What's the goal? So you could think of the power series as like the directions, right? The power series gives us the base directions for a specific function. So in this case, that's going to be f of x, which is the function, right? Equaling the natural logarithm of 1 minus x, which equals the negative summation from k equaling 1 to infinity for x raised to the power of k over k. And then we're given an interval. The rule, and that's the interval right here, this is the rule, this only works if x is between negative 1 and 1. The problem is asking us to make a slightly different version of the directions. It's asking us, it's asking us to substitute. So mathematically speaking, we're going to substitute 5 times x, which is right, oh yeah, right here. 5 times x in the spot where x was. So let's write out the summation. It's a negative summation. So the negative summation from k equals 1 to infinity. And, well, we have x raised to the power of k over k. And this is going to become the negative summation as from k equaling 1 to infinity. But instead of x, we're going to plug in 5x, and we're going to raise that to the power of k. This is going to be over k. So again, the interval of convergence is like the safety zone where the math, it doesn't explode because it's the safe zone in which where the values for the series converge. So anything that is outside of the interval of convergence will make the series diverge, either erratically oscillate in a way not um, that's unpredictable, or go to infinity. If it converges, it approaches a finite sum. Now, that said, the interval of convergence here, it's now going to shift because before, when it was an x, you had the x needed to be between -1 and or equal to -1, um, and less than +1. Well, now the rules have shifted slightly in that it needs to be um, -1 needs to be less than or equal to 5 times x, which needs to be less than 1. So in order for us to find out what x can be, we just divide the whole inequality by 5. So if we divide the entire inequality by 5, and then we put it into proper interval notation, if you have like a less than or equals to sign here, it's going to be like a bracket, which means we're going to include the value. So let me just be specific here. I'm gonna divide the entire inequality by 5, and this is going to become -1/5, which is going to be less than or equal to x, because we got rid of the 5 here, which is going to be less than 1/5. Okay, so now the less than or equal to sign is always going to be a bracket because it indicates that we're going to include this term within the interval of convergence. So -1/5 is included in the interval of convergence. But since we have just a less than sign, it's not less than or equal to, it's just less than, that indicates that this term here is not included within the interval of convergence. So it has to be less than 1/5, not including 1/5, but less than 1/5. So that's just going to be 1/5 with a right parentheses. So this will be our interval of convergence. Yeah, that will be our interval of convergence. This is a three-part problem here. Hold on, I'm gonna get some water. This is a three-part problem here. I guess we could read it all off. So the first thing that we're to do is to find the linear approximating polynomial for the following function that's given, um, that's, uh, so to find the linear approximating polynomial for the following function at the given point A, which A is, if you look, A is 0, and then the function is e raised to the power of -x. And um, to approximate it as at e raised to the -0.6 power. And then part B is to find the quadratic approximating polynomial for the following function centered at the given point A. And then um, part C is to use the polynomials obtained in part A and B to approximate the given quantity, which is here. So what's the goal? I mean, like, sometimes it's like you look at this stuff and you're just like, wait, what? So for me, I try to break it down because I want to know what I'm doing. I feel like that's easier with information retention than to just start plugging things in. Even if it's right, to know what you're doing, I think is probably the best thing, at least for me. So, what's the goal? Well, we need the Taylor polynomial formula. We need the Taylor polynomial formula, and we need to find these polynomials. We need the function and we need the function's derivatives. And it's going to be evaluated at this point. It's the center point, which is a equaling 0, so it's centered at the origin, I'm pretty sure. So we need a few formulas, and well, the first formula is going to be the linear formula, so p sub 1, and that's given here. Uh, p sub 1 of x equals f of a. So function evaluated at a. Well, we have our function. We're going to evaluate it at a. That means we're going to plug in 0 for it, which means that we're just going to be raising e to the power of negative 0. So that's a little spoiler alert there, but this is not the whole formula. F of a plus, and this is why we need the derivative, f prime of a times x minus a. All right, so that's the first formula that we need. This is the linear one. The second formula that we need, um, that's going to be the quadratic formula. Or no, not the quadratic formula, that's something else. Quadratic. This is going to be the quadratic for um for p sub 2. And that's going to be p sub 2 of x equals f of a plus f prime of a times the binomial x minus a plus f double prime, this is the second derivative here, of a over 2 factorial um, times the binomial x minus a raised to the power of 2. So the first step that we would need to take at this point, oh yeah, and let me just underline this. The first step that we would need to take at this point is to find the derivatives. So we have the function given to us as f of x, and f of x equals e raised to the power of negative x. And we need to evaluate it at f of a, which is really f of 0 because we know that a is set to 0. So that means that we're going to be evaluating, well, e raised to the negative 0 power, e just raised to the power of 0, which anything raised to the power of 0 is always 1. So that's our function evaluated at 0. Now we need to find the actual derivatives themselves. So f prime of x, f prime of x equals, well, to find f prime of x, we need to take the derivative of e raised to the power of negative x. But the derivative, let's see here, e, not even, I don't even have to put a negative. E raised to the power of, here's the formula for that. E raised to the power of a times x equals a times e raised to the power of a times x. This is just a standard rule for differentiation. This is just how you evaluated the derivative of Euler's number when there's a coefficient in front of x, and that is when it's being raised to the power of a coefficient that's in front of x. Um, and when you look at this, f of x equals negative e, you might think like, how is there a coefficient? There's a negative coefficient. There's a negative 1 or just a negative sign. So if you take the derivative of e raised to the power of negative x, it's going to be negative e raised to the power of negative x. Okay, I think, right? Yes, I'm pretty sure. But we're interested in we're evaluating it at f prime, so its derivative evaluated at 0. So we need to take that negative e raised to the power of negative 0 or just 0, and anything raised to the power of 0 is 1, but there's a negative sign, so it's negative 1. Then, let's see here. Start back over here. We need to find the second derivative, which is f double prime of x equals negative e. No, we're putting it back through that, and it's gonna start alternating. Because if I take the derivative of negative e raised to the power of negative x, well, that negative sign is gonna come out front again. It's gonna cancel the negative sign. It's just gonna be positive. So e, because we're taking the derivative of what we got for the first derivative. That's how you get the second derivative, by taking the derivative of what you got for the derivative before that. So it's going to be e raised to the power of negative x. Then we'll just have to plug in for f of a, which is f of 0. And then that's going to be e raised to the power of 0 again, which is just going to be 1. So at this point, we're going to plug our findings into the formulas. So since a equals 0, when we look at our formula, both the linear and the quadratic formulas, not the quadratic formula, that's something else, but both for the linear and the quadratic, for both for p sub 1 and for p sub 2, you see that there's going to be x minus a. Well, a is just 0, so we could just ignore that minus a because it's just going to be minus 0. Um, so anywhere where there's an x minus a, that's just going to be x. So we'll start with the linear polynomial. Linear polynomial p sub 1. It's going to be p sub 1 of x equals, let's look at our formula, f of a. We found f of a to be 1 plus the derivative f prime of a. What did we find for f prime of a? Well, f prime of a was found to be negative 1, and then we need to multiply by x. I mean, honestly, we could write it in. We don't have to because it's just going to be x minus 0. So we're just going to ignore that a in the binomial. So we have negative 1 times x. So let's see here. Negative x. So following PEMDAS, we're going to have 1 minus x because multiplication takes precedence over addition or subtraction. So we're going to multiply these two together first, which is going to give us negative x. 1 plus negative x, well, that's 1 minus negative x. Excuse me, that's 1 minus x. Pardon me. So now at this point, we'll do the quadratic polynomial. Um, Quadratic polynomial p sub 2. Let's look at the formula. Well, the first part, we already did the linear part, 1 minus x. So that's going to stay like that. Plus, now we have to look at this formula, f double prime, f double prime of a over 2 factorial. Well, the second derivative, what did we get for the second derivative? Just 1. So it'll be 1 over 2 factorial, but 2 factorial is just going to be 1 times 2, which is 2. And then we plug in mm, x minus a. No, excuse me. X minus a raised to the second power, which is just going to be x squared. So the answer, 1 minus x plus 1/2 times x squared. We could remove those parentheses, but I'm just going to leave them there because why not? Now let's approximate. We have to approximate. You know what? I'm going to get rid of the parentheses. I feel like I don't want to be lazy. There we go. Our answer is 1 for p sub 2 of x equals 1 minus x plus 1/2 times x squared. And then we're prompted to approximate e raised to the power of negative 0.6. To estimate Euler's number raised to the power of negative 0.6, we notice that negative 0. The exponent is negative 0.6, and in our function f of x equals Euler's number raised to the negative power of x. So that means that we need to plug in x equals 0.6 into our polynomials. Not negative 0.6, but 0.6 because e is raised to the power of negative x. So those negative signs are just going to cancel. I mean, I guess for just kind of showcase what's going on, I could plug it in. But let me just let me just show you guys what I'm talking about here. So instead of p sub 1 of x, it's going to be p sub 1 of 0, excuse me, p sub 1 of negative 0.6. Well, we had 1. Yeah, that's okay. We're gonna just plug in 0.6. Those negative signs are gonna cancel, I believe. So in 0.6, there's no point in making it more complex. 1 minus 1, we'll have 1 minus 0.6, and 1 minus 0.6 is the same thing as, well, that's the same thing as 0.4. It's gonna equal 0.4. So then for the quadratic, so this is a p sub 1, that's the linear. For the quadratic, we'll have p sub 2 of 0.6, and let's see, that's going to be 1 minus 0.6 plus 1/2, and then remember everywhere where there was an x, like right here how there was an x squared, it's going to be 0.6 squared, and then that's going to simplify to 1 minus 0.6 is going to be 0.4, and that's going to simplify. So if we have 0.4 plus 1 over 2, 0.6 raised to the second power is going to be 0.36. Okay. Then we have to multiply that back to the fraction. 0.4 plus 0.36 over 2. 36 divided by 2 is 18, I think, yeah. 18 plus 18 is 36. So we'll have 0.4 plus 0.18 And then uh, let's see here, 0.4, but then when you're adding decimals, it's going to go 0.18. And we're going to add those together. So that's going to become 0.58. So our answers for this problem, the linear polynomial is 1 minus x. The quadratic polynomial is 1 minus x plus 1 half times x squared, then approximated at Euler's number raised to the negative 0.6th power. The linear polynomial approximated at that value is going to be 0.4. The quadratic polynomial approximated at that value is going to be 0.58. And so those are going to be our answers to part A, B, and C. It says to determine slash complete parts A through C for the following function, the function being f of x equaling 6 sine of 2x. Now, I didn't write out the individual prompts for A through C. Why? Ran out of gas. I don't know. I probably should have, but I could just, we could just go through we can just go through them one by one. So, part A is to find the first, I think it's the first four. I'm gonna box this. First, find the first four non-zero terms of the Maclaurin series. So we want the first four non-zero terms of the Maclaurin series. So it does disclose to us this is an F. That it does disclose to us that it's a Maclaurin series. I think that's how you spell it. And the fact that this is that well, here, let me see. For f of x. The fact that this is disclosed to us that this is a Maclaurin series is very helpful because that means that we can use wait, oops, that's not what I meant to do. Because that means that we can use table 11.5. So, albeit table 11.5 looks rather intimidating, but actually table 11.5 I've come to learn is actually our friend. And it helps us because it gives us the series for various really important functions, actually. It shows us how we can use an infinite series to describe sinusoidal of x, which is like literally, that's very powerful. That's extremely powerful. And I've come to find out that a lot of the functions that are programmed into the TI-84, like if you're asked to find, various like answers to equations, primarily uses power series. So that kind of just, it sheds some light on the importance of this. Um, that said, we're going to be really focusing our attention to the standard Maclaurin series for sinusoidal of x. So that's going to be sine of x, and let me see here. Let me just be very clear. Well, that's an equal sign, if you can tell. Um, we're going to be looking at this one here. Put a star by it. Sine of x. And so we're going to just copy that down. So this essentially tells us, and I'm going straight for the series here, and then I'll write out the partial sums in a second, but let's just start here. K equals 0, summation from k equals 0 to infinity. We got in the numerator -1 raised to the power of k, which automatically shows us that this is going to be alternating. The signs are going to alternate for the partial sums, times x raised to the power of 2k plus 1. And then on the bottom, in the denominator, we're going to have 2 times k plus 1 factorial, which I think that means that there's going to be some sort of like, there's going to be like this is like for odd indices, I think. If I'm not mistaken, I might be mistaken though. This is going to be equal to x minus, oh yeah, I think it is odd. So x raised to the third, 3 factorial in the denominator there. Plus, there's that presence of the alternating signs. X raised to the fifth, which is odd over like a odd factorial. 5 factorial minus x raised to the seventh over 7 factorial. And then this is going to continue onwards. It's going to continue onwards. And then let's just, before I remove this, so the constraint is that it's for the absolute value of x being less than infinity. Okay. Let's go ahead and honor that. Okay, that's all we needed from table 11.5. Um, so yeah. So all we have to do is find and replace every x in this formula here with 2x. See here, 2x. Because that's what's inside of this, that's sine of 2x. So we have to replace every x with 2x, and on the outside we have 6. So 6 times sine of 2x. So that means that at the end we're going to, oh no, maybe not at the end. That means that we're going to multiply the entire thing by 6. So let's see here. Let's do the first term. The first term is going to be where k equals 0, because we're starting at k equals 0. What's that going to be? K equals 0. K equals 0 is just, let's see, -1 raised to the power of 0 is 1. Wait, what am I doing? Excuse me. Wait. Yeah, 1. Okay. Alright, yeah, okay. Replace x um with replace x with 2x, but then because there's a 6 in front of that sign, there's going to be a multiplication of 6 involved. This is going to be 12 times x. Then we have to find the second term, which is k equals 1. So there's going to be a 6 out in front automatically. But then everywhere, so we're going to look at the second term here, which is going to be negative x raised to the power of 3 over 3 factorial. And then same thing, like everywhere that there's an x, we're going to put 2x, and then we're going to have to raise that to the third power. That is a 3, believe it or not. So we got negative 2x raised to the third power over 3 factorial. And then we're going to simplify this. 6 times 2 raised to the third power is going to be 8. And then x raised to the third power is just going to be x raised to the third power. 3 factorial is going to be, we could do this right here. Let's put like a comma. 3 factorial equals 1 times 2 times 3, which is 6. So 3 factorial is 6, right? Then, well, these 6's here are going to cancel, and we'll be left with negative 8 times x raised to the third power. Then we can go ahead and find the third term. And then the third term is going to be k equals 2. So for k equals 2, we're going to automatically multiply it by 6, but then we're going to like investigate this term here. So we have to, wait, what am I doing? Why am I doing that? No, excuse me. We're going to investigate this term here. We're going to be raising it to the 5th power over 5 factorial. So 6 times 2x raised to the 5th power over 5 factorial. All right, and then 5 factorial here is going to be 1 times 2 times 3 times 4, which is going to be 24. That means that we're going to have, wait a second, something's not right. 5, this is going to be 24, but 24 times 5. So 5 factorial is 1 times 2 times 3 times 4 times 5. So we have 24 times 5, which is going to be 120, right? I think. 6 times 5 factorial, so this is going to be, at least there's not going to be any cancellation here. So it's going to be 6 times, 2 raised to the 5th power is 32. X is going to stay raised to the 5th. 5 factorial is, we calculated 120. And then, um, 6 and, so 6 multiplied, 6 times, no, 6 divided by 120. 120 divided by 6. 6 times 20 is 120. So these are gonna cancel, but like not all the way. 6, so 120 divided by 6, let's see, 2, 4, 6, 8, 10, 12, yeah. So this is gonna be, we can simplify this to, it's gonna be 32 times x raised to the 5th over 20. And then we can simplify that fraction, which is, they're both divisible by 4. Let me be very clear. Divided by 4, divided by 4, I think, right? And this is going to simplify what? 32 divided by 4 is 8, right? Because 8 plus 8 is 16. 16 plus 16 is 32. Well, 20 divided by 4 is 5. 5, 10, 15, 20. And then this is going to be x raised to the 5th on the end of that. Then we have to do the 4th term. Which is k equals 3. So automatically multiply it by 6. Due to the presence of the 6 on the outside of the sine function, this is going to be negative 2x raised to the 7th power over 7 factorial. Okay. what is 120? 120. So we gotta do 7 factorial. So 7 factorial equals 1 times 2 times 3 times 4 times 5 times 6 times 7. So my thing is like 120 times 6 is gonna be what? 24. Something's not right. Hold on, wait. I just miscalculated something. Wait, so 5 5 factorial is 120. Then 120 times 6, it's gonna be 72, 720 times 7, which is gonna be um 5,000. Wait, hold on, let me 5,040. And then this is gonna be, oh, but this is gonna be negative. I'll just put a negative up here in the numerator. Um, 2 raised to the 7th power is 128. X raised to the 7th power is x raised to the 7th power. Um, I think, and then there's also like some simplifications that we could do. So if we wanted to simplify this fraction, let's see, is 5,040 divisible by 6? Indeed it is. Indeed it is. So we could put an 840 in the denominator because we're just gonna divide it by 6 and just get rid of that 6. So there will be cancellation, just not all the way in the denominator. Um, and then in the numerator, it's gonna be 128 times x raised to the 7th. And then we could simplify this further. I don't even know what they're both divisible by. 8. They're both divisible by 8, right? 128 divided by 8, and then 840 divided by 8. Yeah, they're both divisible by 8. 8, oops, 8 and 8 equals, what is this? What is this? Negative 16 over 105 times x raised to the 7th power. That means that we have effectively found the first term, the second term, the third term, then the fourth term. So the next part is part B, and part B says that to write out the power series using summation notation, and now we just look at the general rule what we did um for what we did, right? Like we have the general rule. We know the summation notation for sine of x. Um, so essentially it's asking us to just put this into summation notation. We took the standard sine sum and we plugged it into our specific values. That is the value 6. Oops. Can I use that? Oh, maybe. Not really. Hold on, wait. 6. There we go. That is the value 6 sine of 2x. Um, and so we could write that as the summation from 0 to infinity of uh of 6 times this function here within the summation, the original sine of x summation, except everywhere there's an x, we're going to put a 2x. So everything's literally going to be the same. It's going to be negative 1 raised to the power of k times 2x instead of x. So and I'll just put 2x here instead of x. Still raise to the power of 2 times k plus 1. And that factorial is just going to stay the same. There's not anything that's going to change with that, with the denominator. So this would be how um, to write the power series using summation notation. Now, part C, part C is the prompt is to determine the interval of convergence. And the great thing about working with sine and cosine is that they're both um, infinitely smooth no matter what, right? Like sine wave. It's infinitely smooth no matter how big or how small the x value is. What that means is that the interval for convergence is going to be um, everything. So negative infinity to infinity is the interval of convergence. So to reiterate, the first the first non-zero value for our function, the first four non-zero value, the first the first four non-zero terms of the Maclaurin series f of x equals 6 sine of 2x. The first at k equals 0 is going to be 12x. The second term at k equals 1 is going to be negative 8x raised to the third power. The third term at k equals 2 is going to be 8 over 5 times x raised to the fifth power. The fourth term is going to be the fourth term k equals 3 is going to be negative 16 over 105 times you guys, I think I need to go to sleep soon. You guys ever like if you stay up all night or something, like your immune system just starts shutting down? Anyway, so uh the fourth term at k equals 3 is going to be negative 16 over 105 times x raised to the seventh power. Then to write it out in summation notation, we have let me be clear, that looks like a 1. It's supposed to be a parentheses. We have no, I gotta make it symmetrical here. We have for the summation notation for 6 sine of 2x is going to be k equals 0. The summation at k equals 0 to infinity for 6 times negative 1 raised to the power of k times 2x raised to the power of 2 times k plus 1 over 2 times k plus 1 uh, quantity, and it's a factorial. So 2 times k plus 1 factorial. And then the interval of convergence, just due to the simple fact that we're working with sine function, it's going to be negative infinity to infinity. And this would be the same thing if it was a cosine function. For C specifically, is that the interval of convergence for cosine is going to be negative infinity to infinity, but I digress. We're dealing with sine here. And so that's the interval of convergence. And just to be clear, I'll write I. This problem says to use the correct Taylor series to find the first four non-zero terms of the Taylor series for the following function that's centered at 0. 3x times arctangent of x squared. This is also a Maclaurin series due to the fact that the function is centered at 0. And in order to solve this, we need to first identify what the base series is. So we need to know what the standard Taylor series that's centered at 0 for arctangent is, and we can do this by using table 11.5. In order to identify the base series for the standard Taylor series that's centered at 0, we can use table 11.5. Arctangent is given to us right here, where the blue star is. It's inverse tangent. Let's look at what's going on. So when we look at the table, we can see that arctangent of x, it equals x minus x raised to the third over 3 plus x raised to the fifth over 5 minus something. So it alternates, and we know this because of the -1 raised to the power of x, and then the x squared times k plus 1 that's present in the exponential place attached to this x, the base x, and also in the denominator, tells us that these we're going to be dealing with odd numbers, and we know this because we can see 3 and 5, so we can assume that 7 is going to come next, right? So let's just write this out. Let's just write this out. Um, arctangent of x, and I'm just rewriting what's in the table at this point, but I'm going to add on to it because from the table we know what's going to happen next by just following that particular pattern. No, wait, hold on, I messed something up. This is supposed to be subtraction because it's an alternating series, which is indicated by this -1 raised to the power of k. So that's going to be minus x raised to the 7th, and that's going to be over 7. And then if we wanted to keep going, we would do plus 9, but we're only asked for the first 4 terms. Let's see, first four non-zero terms. So 1, 2, 3, 4. This is going to continue. Um, it's going to continue, and we'll just write out the summation of notation for this as well. Oh, hang on. No, see, I gotta finish this proper. Ellipses plus -1 raised to the power of k times x squared times k plus 1. And then the denominator 2 times k plus 1. And then we can write out the summation notation. Hey, so much for my star. Oh no. There we go. That's an equal sign. Oh man. Um, Let me just write out the function on the inside here. And then such is true for the absolute value of x being less than or equal to 1. Okay. At this point, we can see that, well, not only do we have a 3x out front, not only do we have a 3x out front, but the function that's being evaluated, the arctangent of x, it's actually arctangent of x squared. So we have to replace every x in the base series with our inner function. We'll address this coefficient, we'll address this 3x on the outside of the arctangent function. We'll address that in a second. But the main concern at this point in time, I do believe, it's replace every x in the base series with the inner function x squared. So we'll go ahead and we'll just start rewriting this. We're just gonna go in and rewrite this. Right. So but this is gonna become parenthetical. Um and no, hold on, I messed up. My bad. We gotta be really careful here. X squared raised to the third power. And then here, x squared raised to the fifth power. And then here, x squared raised to the seventh. And that's going to do it for the first four terms. Of course, now we have to use the exponent rule. And so, well, the exponent power rule says that if you have x raised to some power a, which is also raised to some power b, that's the same thing as x times, x raised to the power of a times b. So that means that we can go ahead with a simplification. And so, well, 2 times 3 is going to be 6. So now we're going to have x raised to the 6th. This is still going to be over, still going to be over 3 though. Then we're going to have plus, because it alternates, x. Well, this is going to be x raised to the 10th power, still over 5, minus x raised to the 14th power over 7. Well, we're concerned with the first four terms, but um, so the next thing that we would have to do is to apply, well, the last thing that we would have to do is to multiply the entire series by that 3x, which is out front. So we're going to get 3x times x squared minus x raised to the 6th over 3 plus x raised to the 10th over 3, no, over 5, excuse me, minus x raised to the 14th over 7. And that's all going to be in the parentheses. Oh, wait, hold on. And these are the first four terms, but we could continue onward because it's an infinite series. So yeah, guys, that's going to be the answer for this one. Now, so for this one, it says to evaluate the following limit using Taylor series, and it's the limit as x approaches 0 for 1 minus x quantity minus Euler's number raised to the power of negative x over 5x squared. So evaluating limits with Taylor series is a very clever way to avoid multiple rounds of L'Hopital's rule, where of course you take the derivative of the numerator and the denominator when you have an indeterminate form of 0 over 0. Now, for this problem, we're going to use the series for e raised to the power of x. So let's see. We're going to use a series for, oh, all right. e raised to the power of x series, which is a Maclaurin series. It's a Taylor series, I know that, but basically for this problem we're going to use the series for e raised to the power of x, and we're going to adapt it to fit the negative x that we see present here in the numerator. So let's look at our table so we can investigate the um, the series, the Taylor series that's for e raised to the power of x, which I do believe. Oops. Nice. Something's fine. I'm gonna have to edit this, dude. Now so we're gonna look at this table, and I do believe that. So this is centered at 0, as this is a Maclaurin series. So like let's just check out what's going on here. So we got e raised to the power of x right here in table 11.5. Um, and so we can see the Taylor series for e raised to the power of x. It's the standard Maclaurin series, and it goes, looks like it goes like this. E raised to the power of x equals 1 plus x plus x squared over 2 factorial, and then it says that it goes all the way up to some number k. So for us, let's just go ahead and they're gonna extend it out. I brought up to the third power over 3 factorial. Um, and then all the way up to x raised to the power of k over k factorial, some number k. And to get e raised to the power of negative x, we're going to substitute in a negative x for every x. So now this is going to become e raised to the power of negative x, and well, we're going to keep that 1, but then we're going to have plus negative x, so really just minus x, but you know, we're going to leave that as is for now. Plus we'll have a negative x in the numerator raised to the power of 2 over 2 factorial plus um everything in between. Well, and then just look at this for a second. Okay. Um Everything in between all the way up to some, yeah, let me just honestly, I'm just going to go ahead with a simplification with this. So we're going to have, instead of 1 plus negative x, we'll just put 1 minus x, and then plus negative 2x. Honestly, hold on. Wouldn't that be negative? Wouldn't that be wouldn't that be like minus? No, it wouldn't, because this is gonna get squared out. Yeah, okay. Just kidding. Did I say that it's gonna be minus? Guys, I'm just kidding. I know basic algebra, I hope. So, okay, this is just gonna be x squared. It's gonna be, because it's x squared. So if you square anything, if you multiply two negatives together, it's always gonna be a positive. So that's why that's like that. But this is gonna be a minus. Here, if we went up to like x raised to the third power, this is going to be still subtraction because now it's raised to the third power. So you're doing a negative times a positive. No, you're doing what am I talking about? You're doing a negative times a negative, which is a positive, times a negative, which is a negative. So that's why it stays like that. Um, and then let's see, this is going to be 3 factorial. Um, but then that's going to be 1 minus x plus x squared. 2 factorial is 2 minus 3 factorial, which is 6. And then this is going to stay negative x raised to the third power. So at this point, we're going to look at this and we're going to be like, okay, well, we're going to substitute this into the limit. So we're going to plug this series into the numerator of our limit. And well, I think we actually got everything that we needed from this table here. So we're gonna just kind of vacate it. Yeah, and then we can grab some room back, I hope. Right? Um, and so now we're gonna plug this into the numerator. So what does that look like? Well, we got the limit as x approaches 0 for 1 minus x, well, yeah, well, maybe I could do a side by side and just kind of show why we want to do this. I think that might be the move. So I'm just going to rewrite this to do a side by side just because it sort of helps me compartmentalize things um, and explain it. Now, if we were to just like look at this as is, now we are going to plug in this here, what we found um, into the numerator. But let's just like understand why. So we want to take the limit. So basically, evaluating limits with Taylor series is a way, like I said earlier, to avoid using L'Hopital's rule. When we can use L'Hopital's rule, we can only use L'Hopital's rule if we have an indeterminate form of the form 0 over 0, which we would get if we plugged in 0 everywhere where we see an x in this rational expression here. We're going to have 1 minus 0 minus, let's see, yeah, 1 minus 0, 1 minus 0 minus 1. So 1 minus 1, which is going to be 0. And then on the bottom, 5 times 0 squared is going to be 0. So it's going to be an indeterminate form. But we don't want to use L'Hopital's rule. We can avoid it by using the Taylor series. So that is why we're going to rewrite the limit as x approaches 0 as follows. That numerator, what we found for the numerator, or what we stole from the table and then found for the numerator, because I'm not going to act like I memorized those formulas. um X squared over 2 minus x raised to the third power over 6. I don't have to memorize the formula for my calculus class, but a lot of people do. A lot of professors, like older like professors, I'm not calling you guys old, but like a lot of the professors from before the younger generation who did mathematics had to memorize all those formulas. Like, let's just take a minute to recognize that. These people, they had to memorize these. Now they give it to us on the test. So here's a head nod to the OGs. So we're going to put this over 5 times x squared. And so, yeah. But then now we could simplify the numerator and how we can watch how the first few terms are going to cancel out. Oh, gosh. I just messed something up. I just plugged that into the numerator. I totally ignored the fact that there's a 1 minus x right here. 1 minus x. Then then we plug it in for the e raised to the power of negative x. So minus, that's going to stay the same. Then we plug this in, you guys. Then we plug this in. So then it's going to be 1 minus x plus x squared over 2 minus x raised to the third over 6. Put our ellipses there. And then we're going to have 5 times x raised to the second. Now we could see how the first few terms are going to cancel out. We're going to look at this and we're going to say there's going to be a couple terms that cancel once we drop these parentheses. And that's going to go like this. So 1 minus 1, it's going to cancel. Something's wrong. What did I do? I just like messed something up really badly and I don't even know what I did. Wow, I really messed this up. What did I do? I actually don't know what I did, you guys. I have no idea what I did wrong. I did something wrong. I do know I did something wrong. Something is off. Something is not right. Hold on, let me just look at this really quickly. 1 plus. Is that not gonna just become that's negative E? Everywhere where there was an X, we plugged in. I have absolutely no idea what's going on right now. Absolutely no idea what's going on. I'm freaking out right now, you guys. I don't know. I'm freaking out. You guys, my voice sounds calm, but I'm freaking out right now. I don't know what I did wrong. There's something that's not right here. What if I switch this? Like realistically, what if I switch this? So we have negative X plus 1. That's not gonna do anything. Oh my God, I'm freaking out, you guys. I don't know. Here's my question. What? Wait, like, okay, so I don't understand, like, how. Let's just play around with this. Let me just play around with this. I'm gonna play around. Oh, oh, okay. I'm gonna play around with this in like this like fairy pink color. No, I don't want to use pink. I like the color blue. Guys, my favorite color is blue. Anyway, no one cares. So let me just let me let me just like play around with this. Okay, okay. Maybe I plugged it in wrong. Maybe I plugged it in wrong. When you plug in, you're supposed to use parentheses, and I just didn't. I just like shoved it on in the numerator, and I did it wrong twice. So I think so. I did it wrong the first time. I did it wrong the second time. Let me just see here. Oh my God! Wait, what's going on? 1 minus x, um, minus, and we're gonna stick this in the numerator. This is wrong. Like I don't even want to look at this. Well, no, I'll put like 1 mark through it just because I want to be able to see what I did wrong. Let's just like throw this in parentheses and just kind of see what happens. So now we have, there we go, because now that might get distributed. So 1 minus x plus x raised to the second power. Um, and then there's going to be some sign changes in there. I don't know if this is right, you guys. I'm literally just like winging this. Like I'm just trying. Mm, hmm. Raised to the third over 6 plus some all the way up to some number. And I'm not even worried about the denominator right now. I'm just like, this numerator um is just something like that's going on, you guys. So if I distribute that to each term, that negative sign, I'm gonna get the limit as x approaches 0. Um, 1 minus x minus 1 plus x minus x squared, because there's gonna be some sign changes, right? Ooh, I don't know if this is right, guys. What? I'm just gonna leave this as a plus because we can't really distribute it to like hypotheticals. Let me just like look at this for a second. This actually is much better. This is wrong. All right, this is wrong right here. Um and I think what's in blue is correct. Let's see. Drop those parentheses. You're gonna have 1 minus 1. Those are gone. Negative x plus x, those are gone. Then what's up in the numerator? The limit as x approaches 0. Um, well, now it's going to be negative x squared over 2 plus, dude, did I really put an x squared here? This is supposed to be x raised to the third. I'm sorry. But this part's still correct. Um, so yeah, so negative x squared over 2 plus x raised to the third over 6 plus something. Honestly, we could roll. Let's add on. Why not? We know it's gonna be negative. We know it's gonna be negative, so it'll be 4 factorial. Let's see, 4 factorial is gonna be 24. So if we put 4 factorial, so this is gonna be 24 down here, and then up top it's gonna be x raised to the fourth. So we could just sort of extend it outwards for fun, just to give it a little bit more bulk. Um, at 5 times x raised to the second. And so that's what the new limit's gonna look like, I think. I'm pretty sure. Mm. So let's just run with it and let's try to evaluate this. Let's try to evaluate this. Um, to evaluate this, we need to um divide each term in the numerator by what's in the denominator. So we have the limit as x approaches 0. Let me see. Dude, this problem's a curveball. I thought this was gonna be easy. This problem is actually I mean, none of it's easy, but I didn't expect this. Okay, so well, let's just break it up. Let's just break it up. We're gonna introduce some complex fractions here. Let's see. Split up the fractions. 5 times x raised to the second on the bottom. So we're dividing this right here. Negative x raised to the second over 2. We're dividing that by 5 times x raised to the second. Um, plus another complex fraction. So we're just gonna grab that second term in the numerator. X raised to the third over 6, and then we're going to divide that entire thing by um, 5 times x raised to the second, and then minus well, same sort of idea here. Uh, X raised to the fourth over 24 divided by 5 times x raised to the power of 2. Um, what do we want to do with this? Well, tell you what, I need room. We could just put this right here. I'm gonna leave the mistake in there. I think it's good to see mistakes sometimes, because then you can learn from them. Because, yeah, you know, I don't want to make that mistake again. So, mm, let's reciprocate x squared over 2, negative x squared over 2 times, well, 5x squared over 1 plus x raised to the third power over 6 5x squared in the denominator here over 1 because this is us reciprocating minus um x raised to the fourth over 24 times 1 over 5 times x squared. Yeah. Oh. Um yeah, there's gonna be more going on. This is a and really oh yeah, true. Remember this is we're doing this for everything. We just don't have to write it in. I'm just writing out like a few terms just to sort of see what's going on. Um, okay. Well, let's see what's going on here. X squared are going to cancel here in this term. Well, this is going to become x raised to the first. These x's are going to go away. These x squares is gonna cancel out. This is going to be now x raised to the second power. Um, so now so now gosh. Okay, well, we've effectively divided each term. So this is going to become okay, wait. X raised to the I'm sorry, guys. My brain is everywhere. Wait, the limit as x approaches 0? Um, um, the limit as x approaches 0? Well, 2 times, so this is going to be, okay. So we're going to do negative 1 over 2 times 5. So negative 1/10 plus, well, there's one more x left, right? Then we're going to do 6 times 5 is 30. So x over 30 minus, because it alternates. Let's see. Negative x squared over 24 times 5. Gosh, what is 24 times 5? 24 times 5. Um, 24 plus 24 is 48. 48 plus 48 is 96 plus another 24. 120. So then 120 plus whatever, right? Not whatever, but the next terms in the series. So now I think the next thing to do is to of just evaluate the limit. Just evaluate the limit. So as x approaches zero, as x approaches zero, we're gonna plug in a zero to everything that has an x in it. Oh wow. Oh wow, guys. Okay. Okay. Yeah. If we plug in zero to negative 1/10, it's just gonna be negative 1/10. And then um if we plug in zero for everywhere where there's an x, it's just gonna be zero. Zero divided by like 30 is gonna be zero. Zero divided by um well, 0 raised to the power of 2 is 0, and then divided by 120 is going to be 0. So it's literally going to be 0 for everything except for the first term. So what does that mean? Well, that means that the limit as x approaches 0 for, let's see, 1 minus x quantity minus e raised to the negative x power minus e raised to the power of negative x over 5 times x squared, this is going to equal negative 1/10 because negative 1/10 is the only term in the limit now that doesn't have an x in it. So as x approaches 0, every term with an x in it is going to become 0, and the only thing left is the constant term at the beginning, which is negative 1/10. Therefore, the limit is negative 1/10, and thus the answer is and thus the answer, sweet victory. I can't even circle it. The answer is negative 1/10. Let's do the next problem. The next problem in the problem set says to determine the radius and interval of convergence for the following power series. The power series being the summation from k equals 1 to infinity for negative 1 raised to the power of k, which indicates that it's going to be alternating, um, times x raised to the power of k over 4 raised to the power of k. Um, well, this is a power series where I think the way to go here, everything's being raised to the power of k. We have this negative 1 is raised to the power of k, this x is raised to the power of k, and this 4 is raised to the power of k. I think that we could use the ratio test. Um, since we have k in both the numerator and the denominator of this fraction here, and the x and the 4, I think that the terms will simplify. And so, hold on to get my sensitivity right. Um, so let's run that ratio test. So that means that let's say the limit equals L stands for limit. So L equals the limit as k approaches infinity, the absolute value of a sub k plus 1 on the top, and then a sub k on the bottom. That's a sub k. Hold on. It's a subscript. A sub k. Absolute value. And so we take the limit of a sub k plus 1 on the numerator and then a sub k in the denominator. We take the absolute value of that as the limit approaches infinity. And what's that going to tell us? It's going to tell us that if the limit is less than 1, then the series converges. But then if the limit is greater than 1, if the limit is greater than 1, the series diverges. And then if the limit equals 1, then the test is inconclusive. And so that's going to be the ratio test. So then we want to know, so for ours, should I box this? I'll box it. So for us, a sub k is, I think it's -1 raised to the power of k times um x raised to the power of k over 4 raised to the power of k. And then to get a sub k plus 1, everywhere where there's a k, we plug in k plus 1. So -1 raised to the power of k plus 1 times x raised to the power of k plus 1 over 4 raised to the power of k plus 1. And then that's going to set us up for the limit, no, excuse me, for the ratio test. So for taking the limit, um, so we'll take the limit from as k approaches infinity of the absolute value. Oh, this is going to be a very complex fraction. I'll try to squeeze it in there. -1 raised to the power of k plus 1. That's not, yeah, k plus 1 times uh x raised to the power of k plus 1 over 4 raised to the power of k plus 1. Then the denominator, it's going to be -1 raised to the power of k times the rational expression x raised to the power of k over 4 raised to the power of k. And then let's reciprocate for simplification purposes the limit as k approaches infinity. Hmm. I'm trying to think about how I'm gonna I think I'll go, wait, no. Ooh, oh man. All right. I'm gonna just do this clean. I'm not gonna reciprocate yet, you guys. I'm a simpleton. I have to do it like this. Ooh. Yeah, guys, I'm a simpleton. I can't do I can't do mathematical trick shots with this. I have to keep this very organized. Um, yeah. We're not gonna reciprocate yet. I have to line this up right. There will come a day for mathematical trick shots, guys, but it's not today. All right, now we'll reciprocate now that this is organized for my simple mind. Okay, this is okay. Only now, only now can I continue to work through it. Okay, um, so this is gonna be -1 raised to the power of k plus 1 times, can I work through it? X raised to the power of k plus 1 over 4 raised to the power of k plus 1 times the reciprocal of what's in the denominator. 4 raised to the power of k over -1 raised to the power of k times x raised to the power of k. Um, so now, let me just g-check this. Yeah, I think that's right. Um, I'm gonna regroup into um into three separate rational expressions in the absolute value bars just because like I I don't know. It's just easier for me to conceptualize. The limit as k approaches infinity for. So how do we want to regroup this? I think that all the bases should go together. So we're gonna have three separate fractions. Um, what did I do that for? I don't even know what I'm doing, you guys. Wait. -1 raised to the power of k plus 1 over -1 raised to the power of k times. So these bases are gonna go together. Um, say we'll do the x's next. So we'll have x raised to the power of k plus 1 over x raised to the power of k times 4 raised to the power of k. Sorry, I was thinking about something else. 4 raised to the power of k plus 1. And uh yeah, now I think we can apply one of the laws of exponents. X raised to the power of m over x raised to the power of n equals x raised to the power of m minus n. Okay, just a law of exponent. It's right there. One of the laws, at least. Try to line that up. Um, wait. So now I think that we could write this as the limit as x approaches infinity for the absolute value of -1 raised to the power of k plus 1 minus k times x raised to the power of k plus 1 minus k times 4 raised 4 raised to the power of I think this one needs to be in parentheses. Uh 4 raised to the power of k minus k plus 4. No, play k plus 1. I don't know why I got 4. I'm thinking about something else, guys. All right, let me just refocus. Focus, focus, focus. Right. Um, and so we could simplify this. The limit as k approaches infinity of, so this is going to be the absolute value of -1 raised to the power of 1, which is going to be negative 1 times x raised to the power of 1, which is just x, times this negative sign is going to get distributed. So it's going to be minus k minus 1. Well, that's going to be, you could just write this as like 1/4, right? Because it's going to be negative raised to the negative first. But then, why would we write it as that when we could write it as 1/4? We could simplify this further. The limit as k approaches infinity of the absolute value negative x over 4. But it's an absolute value, so we're only interested in the distance from 0. So it's going to be the limit as k approaches infinity for x over 4, right? No, not exactly. Not exactly. Because we could leave it like this. We have to put absolute value brackets on that x to leave that as the absolute value of x over 4. So we have the limit as k approaches infinity for the absolute value of x over 4. But for convergence, we know that for convergence, the result needs to be less than 1. So, so the absolute value of x over 4 has to be less than 1. Okay, well, let's do some algebraic manipulation with this here. If we divide both sides, no, not divide. If we multiply both sides by 4, we're going to get the absolute value of x is less than 4, I think. And so that would mean that the radius of convergence, say the radius of convergence is it's going to be r equals 4. And then now we have to check the endpoints. So um what happens at the boundaries? So like so 4 is the radius of convergence. But what happens at the endpoints? Like what happens at the boundaries? What happens when x equals 4 and what happens when x equals um negative 4? So we're going to test x equals 4 first. It doesn't matter which one we start with, but we're going to start with x equals 4. So we'll substitute 4 for x into our series. And well, that's going to look like this. The summation as k equals 0, the summation from k equals 0 to infinity of negative 1 raised to the power of k times not x raised to the power of k, but 4 raised to the power of k. And let me make it in parentheses, 4 raised to the power of k over what? 4 raised to the power of k. Okay, and that's just going to be a form of 1, right? Interesting. So then that means that this is going to be the summation from k equals 0 to infinity of negative 1 raised to the power of k. because this is a form of 1. And well, this series is alternating. This is alternating. That's a G. That is the worst. Okay, that is the worst G I've ever drawn in my life. Uh, it's alternating because of this here, -1 raised to the power of k. And so that means it's going to be like -1 plus +1 minus 1 plus 1, um, and so on. And that's because the limits of the terms, and because the limits and okay, so this is alternating, and because the limit of the terms is not 0, it diverges by the divergence test. So remember, the only way that a series has any shot at convergence is if the partial sums start to go to 0. And so if they start going off and they're getting larger and larger, then they're gonna add up to infinity. If they start getting smaller and smaller and smaller, then they're gonna have a finite sum. Now we're going to test. So we tested um, x equals 4. So let me just be clear. This diverges by the divergence test. Because again, we know this intuitively speaking because the limits of the term because the limit of the term okay, so when we tested x equals 4, the limit of the terms is not 0, so it diverges by the divergence test. Now we're going to test as x equals 0. Excuse me, not x equals 0, as x equals -4. I don't know why I said 0. My mind is a lot going on. Okay, so uh so we're going to substitute into the series for the same way that we did before. So hold on. Okay. Um, so we'll substitute into the series the same way we did before. So we have the summation from k equals 0 to infinity, and we're gonna have -1 raised to the power of k times the rational expression, but instead of x, we're gonna have a -4 because we're testing for x equals -4. So -4 raised to the power of k over 4 raised to the power of k. And well, let's see. So that's gonna be the summation from k equals 0 to infinity. Um, the summation from k equals 0 to infinity of this is just gonna turn into -1, right? So we're gonna have -1 raised to the power of k times -1 raised to the power of k. And then what's that gonna be? The same thing as um no, wait, hold on. That's the same thing as k. The summation is of k equals 0 to infinity for -1 raised to the power of 2 times k. And we can simplify that further by saying the summation from k equals 0 to infinity is well, that's gonna be we're gonna have 1. We're gonna have 1, I think, right? Yes. because no matter what k is, it's always going to be 1, right? You got 2 times, yeah, so it's negative 1 raised to the power of 2, which is going to be 1. And then 1 raised to the power of anything is 1. So it's a summation from k equals 0 to infinity. It's going to be for 1. But then if you start plugging in for 0 into 1, I mean, we're just going to be doing this over and over again. Nothing's going to be changing in the function. We're just going to be doing this forever. 1 plus 1 plus 1 plus 1 plus 1 plus 1, and we're gonna could do this literally forever, and then that's gonna eventually, that's just gonna be infinity, right? So intuitively speaking, we know that by the divergence test, oh well, 1 plus 1 plus 1 plus 1 plus 1, that's not going to 0. That we're not getting close to 0. We're not getting closer and closer to 0. So um, this is not going to add up to a finite sum. It's not going to converge. That means it's going to diverge. So um, test x equals -4 diverges. And so that means that this diverges by the divergence test. This is the last problem of the problem set. It says to use the given Taylor polynomial p sub 2 to approximate the given quantity and to compute the absolute error in the approximation, assuming that the exact value is given by a calculator, and to approximate e raised to the power of -0.13 using f of x equals e raised to the power of -x, and p sub 2 of x equals 1 minus x plus x raised to the second over 2. So the thing about this problem is it builds directly on the e raised to the -x polynomial that we did earlier. Um, so we're going to use that polynomial to estimate a specific value and to check um to check how wrong the estimate is when compared to the exact value. So we're approximating e raised to the power of -0.13 using f of x equals e raised to the power of -x and p sub 2 of x equaling 1 minus x plus x squared over 2. So let's work on part A first. So part A is to approximate e raised to the power of -0.13. And we're given the polynomial p sub 2 equals 1 minus x plus x squared over 2. And to approximate e raised to the power of -0.13 using f of x equals e raised to the power of -x, we have to identify like what the value of x is. And since the exponent is -0.13 and the function is e raised to the power of -x, we um, we're just going to plug in for x, um, x equals 0.13 because Euler's number is raised to the negative power of 0.13, and f of x is e raised to the negative x. So it's gonna become positive. Um, Now that said, we're gonna substitute x equals 0.13 into p sub 2 of x. P sub 2 of x, which is equal to 1 minus x plus x squared raised to the second power. And then that it's gonna look like something like this, I think. P sub 2 of 0.13 equals 1 minus 0.13 plus 0.13 squared, right? Squared over 2. Um, and then we can like break this down and like, excuse me, I can break this down and try to calculate the terms here. Um, well, let's see. 1 minus 0.13, it's going to be 1.87. What am I talking about? 0.87. 0.87. You subtract 0.13 from 1, you'll get 0.87. Now let's see, as for 0.13 raised to the second power, that's going to be 0.0169. So we'll have 0.0169, I think. Yeah, I think, over 2. Then we have to divide it by 2, so we'll have 0.87 plus, the answer to that is going to be 0.00845. Um, and then we can add them up, right? What if I did that up here? Not to be confusing, but just for the sake of like conserving space, you just have to like line up the decimal point, right? 0.87 over, well, that's not over, this is an addition problem. 0.084554878.0. And that means that the answer to that is going to be 0.8. That looks like a 6. Hold on. 0.87845. And so that's going to be part A. Part B, no, part B, it's going to be, well, we're asked to compute like that, what's the absolute error? And the absolute error, well, here, let me just, what's the absolute error? The absolute error, well, it's like the positive difference between the true value, like what the value actually is, and our approximation. So it's like the absolute error, it's it's the exact value, the absolute value of the exact value minus, that is a big minus sign, hold on, minus the approximation of what we approximated it to be. All right. The absolute error is the difference, is the absolute value of the difference between the exact value and the approximation. So we're asked like to use a calculator to find the exact value of what, we'll say what is e raised to the power of negative 0.13. What is the exact value? So I'm gonna grab my TI-84 here. Say e raised to the power negative 0.13. All right. I my calculator says that this is going to equal 0.80954 309. Okay. But then what we approximated it out to be, let's see, our approximation. it was 0.87845, and to find the absolute error, um we're going to take the exact value 0.878095439, and from that we'll subtract 0.87845, and we'll take the absolute value of that. So I'm going to use my calculator to do this for time efficiency purposes. Okay. And well, I got negative 3. Wait, hold on. This is the absolute value. What am I doing? So so it's the absolute value, so it's going to be positive. So it's going to be 3.5456 9 1, and for proper scientific notation, times 10 raised to the negative fourth power. Um, and then that's going to be approximately equal to 3.5 3.55 times 10 raised to the negative fourth power. And that's our answer. Thank you for watching my video.